Hi everyone, my name is Steve Sclafani, and I'm here to talk about the observation of the galactic plane and neutrinos with IceCube. So IceCube is a neutrino detector located at the geographic South Pole. Shown here on the right is the IceCube lab located on the surface, as well as 5,000 digital optical modules, which are arrayed in this hexagonal pattern on 86 strings, buried a kilometer and a half in the glacial ice. When a particle interacts with our detector, it actually hits the ice and produces light. And these detectors, these DOMs, can uh, detect that light, convert it to an electrical signal, and digitize it. In 2013, IceCube has observed a flux of neutrinos from outside of our solar system. And a lot of the last decade has been dedicated to trying to figure out the sources of the flux of neutrinos that we have discovered. One source is our own Milky Way Galaxy. So shown here is a top-down rendition of artist rendition of our Milky Way. The sun is denoted in the bottom with a star, and in galactic coordinates, 0 would be towards the galactic center, and going from 0 to 360 would be pointing at different sources, features of our own Milky Way. If we were to zoom in, the galactic plane we think is full of cosmic ray sources, which have yet to be identified. When a cosmic ray interacts with one of these sources or accelerators, it will produce neutrinos and gamma rays. The cosmic rays will also escape the source, remain bound by the magnetic fields of our own galaxy, and eventually, hundreds of thousands of years later, interact with a particle of dust or gas and produce neutrinos and gamma rays that correspond to the matter of our own Milky Way. This component is known as the diffuse neutrino emission. So shown here is a few different renderings of our own Milky Way. The top is the image that most people would be familiar with, the image in optical light. If it was a very dark night and very clear skies, you could go out and see the plane of the Milky Way, the stars, dust, and gas. The Milky Way has been observed over many different wavelengths of light, and shown in the second panel is at the higher energies above 1 GeV, the observation by Fermi-Lat telescope. And you can see here some sources that are dotted along in the plane, as well as this overall haze of gamma rays that aligns well with the dust and gas of the top image. So this is the diffuse component that I talked about previously. If we just take this diffuse component, we expect there to be a neutrino counterpart. So we can convert it from the gamma ray observation to the expectation neutrinos, which is shown in the third panel. And this is concentrated in our southern sky. And finally, we smear it with the typical event angular resolution, which for this work is somewhere between 5 and 10 degrees. And this is where we would expect our neutrinos to come from. And this is shown with contours corresponding to 20% and 50% of the signal neutrinos. So this is the signal we searched for, and this work has actually identified high energy neutrinos from the Milky Way galaxy for the first time. So this is at a confidence level of 4.5 sigma after accounting for 3 tests that were performed. On the bottom right here, we see the number of neutrinos, the best fit number of neutrinos as a function of energy for each of the templates, and comparing it to the models. So we can add a new panel to this image. This is now the observation of the Milky Way galaxy and neutrinos reproduced with those same expectation contours from above. Here, darker means more significant. So this is the first observation of the galactic plane in neutrinos. It's actually the first observation of a particle other than light. And this brings us, to the dawn of galactic neutrino astronomy. So on the right here, we see our Milky Way galaxy above the IceCube detector. And now we know that it's producing high energy neutrinos that we can detect at the South Pole. Thanks.